So now let me move to the last part of this talk, which is something that I think it's even maybe more exciting, which is, can we really learn equations and can we learn laws and hypotheses directly from data using machine learning? And the focus here is really to discover powerful models. And the reason we want to learn such equations and models, especially for the scientists that may want to engage with machine learning, is that really, if we are able to provide such governing models, and I'm going to define that in just a little bit, they will enable us to understand variables, relationships, components, as well as experiment effectively with the system. So the focus is really to discover something on the basis of these machine learning models. And often when I engage with people outside our machine learning community, such as the clinical community, and in the past with other communities, they often say, well, we don't learn a lot new from machine learning. And this is partially due to this lack of transparency, but it's also the fact that machine learning, the way in which we are performing it today and doing explainability, it's really inadequate for discovery. We don't just want feature-based explanations and example-based explanations. We often need true equations. Part of the reason people like regressions is because they provide an equation that somebody could be involved with, for instance. So what I would like to start to talk about in the next part of this talk is a new frontier of machine learning interpretability, if you like, but maybe going beyond that, which is discovery. So the focus will be to discover governing equations, which are mathematical models that describe how the known variable changes, the unknown variable changes given one or more of the known variables. And especially I'm going to focus on compact and closed form equations. And the focus here will be on equations that are going to be finite, compact sequences of operations that will have input variables and numeric constants. And the reason I'm going to focus on learning using machine learning such compact and closed form equations is that they are concise, generalizable, amenable to further analysis, they are transparent and interpretable to human experts. And really, if we can do that, then we have achieved what regressions have achieved, but with much better performance. And I'd like to put this discovery agenda on the ladder, and this is not the ladder of my former colleague at UCLA, Judea Pearl, but it's what I call the discovery ladder. So a lot of what you have seen in the previous part of my talk was related to really learning associations. For instance, in the case of medicine, the specific chemotherapy drug is associated with a particular side effect, for instance, liver dysfunction, and I'm making predictions that are going to highlight that effect on the, let's say, the outcome of interest. Of course, the work of Judea Pearl goes one step further and looks at these causal relationships where they learn the graph structures and uncover the role of interventions. For instance, how will the specific chemotherapy drug impact women who have a particular low BMI and how this may lead and may cause liver dysfunction. But what I'm going to argue is that in medicine, we need to go one step further. We need to have quantitative causal effects as estimated and quantified by quantitative analysis. For instance, we will need to unravel from data structural equation, functional causal models, differential equations, and unravel these governing equations of medicine. For instance, we may need to know how in a particular patient the drug may affect the tumor growth over time and assess that quantitatively rather than just qualitatively. So I would say this is the research frontier in discovery. What type of equations do I have in mind? Most of you are already very familiar with equations from physics, whether it is unraveling explicit functions, implicit functions, ordinary differential equations, or partial differential equations. And these are equations we are all very familiar, governing equations of physics. Note that I'm not talking here about the discovery of drugs and molecules. I'm talking here more about physiological processes. And at this stage, you may say, well, you can do that for physics, but is this even possible for medicine? And the answer is yes. The reality is that already we have some governing equations in medicine. For instance, for risk prediction, there is a model called NHS Predict that's often used for prediction of breast cancer equations. And for instance, we can estimate the cumulative hazard for breast cancer mortality after a certain number of years after surgery. This is an example of such a governing equation. In pharmacology and physiology, we have the Hill equation. For disease progression, we have a very famous paper by Gang and al. That appeared in Nature that looks at the role of chemotherapy and radiotherapy on tumor growth. And in epidemiology, we have heard in the era of COVID-19 a lot about SIR and SER models. And this represents, if you like, the governing equations of how disease spreads in a population. But the reality is that in order to discover such equations, we required humans. So these equations were not discovered by a machine learning model. All the equations that I showed to you were discovered by humans, by human scientists, whether I'm talking about physics, the physiological, or the psychological. So the reality is that in order for these equations to be discovered, we need scientists that have brilliant insights, intuition, and domain knowledge to really tease out from data, from the underlying data hypothesis, and then validate such hypotheses. But I'm going to say that while this is wonderful, has quite some disadvantages. First, we need to wait for an Einstein or a Kahneman to be born. Number two, the current hypotheses that they may put forward may or may not be correct. Let us not forget that for many years, humanity, for many centuries actually, humanity believed the world is flat. And these were theories that were put forward by scientists in the beginning, claiming that the world is flat. So humans are prone to error. Also, the data that they are using to issue a hypothesis may often be selected by them conveniently to further their hypothesis. Also, because we are humans and our computational brains are not fantastic, we only have a few variables that are considered. And we may not select in the right way these variables. And finally, in the case of medicine, things are even more complex because the variables are measured at times in the lab, but not in the real world. So what I'd like to discuss today is how can we move in this agenda in trying to unravel governing equations using machine learning from data. So let us start with learning from data explicit functions. And you have seen here some functions that were learned by humans using linear models and regression models, to which they have added some nonlinear terms by hand. So can we do that in a more principled way using machine learning? So a few years back, partially because we have these very powerful machine learning models based on automated machine learning that were doing a lot better than regression models, we wanted to take our methods to implementation in the clinical domain. And a big hurdle was the fact that we were not having equations. And for instance, in cancer, one needs real equations to take a particular model to the clinic. So we developed this set of methods which are able to take any black box machine learning model and turn it into a white box model. And we do that using symbolic metamodels. And the idea here is that we create models of models, that there is in the word metamodel. And the focus is to take a black box model F and approximate it with a white box function J, and find the representation J which is closest to F in a space that is selected by the user, in a space of models, white box models that's selected by the user. So how can we really do that? So again, the idea is I take a black box model and I'm going to try to let the user decide what is interpretable. It could be that it's, let's say, polynomials, or it could be that maybe if the user is a physicist, there are Bessel functions. So they can decide what is the space of white box models that wants to have interpretations in the form of explicit equations in that desired white box, in that desired white box space, if you like. So again, what we are going to learn is we are going to search in this white box metamodel space for function approximations that are closest to the black box model F. And we are going to learn using gradient descent methods in a very simple way. But the reason we can do that in a simple way is because we have representational spaces that are very powerful. In the initial paper that I've done together with Ahmed a few years back, we looked at Meyer-G functions as a very powerful way to represent different classes of white box functions, whether it's polynomials, whether it's Bessel functions, etc. And then subsequently, together with Jonathan and Yao, we went one step further and we looked at symbolic pursuit, where we eventually are able to create representations and basis functions that are increasingly more complex to be able to approximate the black box model with higher and higher accuracy. And we use symbolic pursuit, and hence the basis is not fixed, like in the case of the paper with Ahmed, but rather the basis may be changing if we want to have better approximations for more and more complex functions, black box models F. Okay, so how does this really work in practice? We can then take a black box model. Here I'm showing to you this black box model that we have defined for automated machine learning called autoprognosis. And we take the black box model prediction and turn it using meta models into a white box equation that creates an explicit equation that we can read. I've not put on this slide the real equation. The real equation you can find in this Nature Machine Intelligence paper, as well as the explanations of the different factors that were found by the model. But what I want to show to you instead is I want to show to you instead how to use these symbolic meta models that have found explicit functions to use for prediction. The way we are going to use them is as follows. We use the black box model, autoprognosis, to guide us to find the meta model. But as soon as we found this white box model J, which is the meta model, we are able to completely throw away the black box model. So the black box model is no longer needed. It's just used as a guidance to be able to help us find the white box model J. That is going to then be used at runtime to issue predictions. So we issue predictions no longer on the basis of the black box model autoprognosis, but rather the approximation of it, which is a real equation using the meta model. And what you can see is that this meta model, which was found in this way, which is a real equation with nonlinear terms though, is significantly better than the white box model, than the prediction model made using regressions, which is the current state of the art used currently in the UK as well as United States for prediction called NHS Predict. So you see the advantages of learning using machine learning, first a black box model, but then we cannot use a black box model. This would not be acceptable for use and for adoption by, for instance, the Joint Committee on Cancer in the United States or by NICE in the United Kingdom. But instead, we can use the symbolic meta-model approach to learn real equations associated with these nonlinear equations, and then issue significantly improved predictions as opposed to regression models that are linear. Also, what you can do then is, I talked before about ways to create this feature interpretability and feature predictions at the personalized level. An advantage of the symbolic meta models is that now we really have even equations that are going to be able to be interrogated And unlike previous models such as Schaar, Lime, Vase, learning to explain, an advantage as opposed to these methods is that now I have a real equation that I can perturb, and I can tell you that as the patient, for instance, loses some of the weight, what will be the impact on the risk for this patient. So I really have a very transparent and powerful model, like regression models would have, to estimate risk and to estimate how risk would change on a particular individual if different types of changes would occur. Yeah, and as I mentioned, we can compute individual feature importance in an analytic way. I talked about explicit functions, but what about something more interesting? Ordinal differential equations. And as I mentioned, this is really the frontier we need in science, and in particular in medicine, because systems are not static, they are dynamic, they evolve over time. So this is a much harder problem. How can we learn all these from data? So the goal is to discover the underlying differential equations from a data set. And in order to do that, let us see how this problem is currently approached today. One way in which you may think that this problem can be addressed is through symbolic regression. Symbolic regression cannot be directly used. You'll need to make some transformation to be able to do that. But even if you are able to do that, such methods suffer from a variety of problems. First, estimating the derivative from data, from noisy data, like we have in reality, in medicine, but always, is hard. That's number one. So often these methods are ineffective. Number two, solving the inverse value problem is computationally intensive and not suitable for chaotic systems, and sometimes it may not even be well defined. So these classes of existing methods are not very suitable to solve this problem. And I'll return to some of the challenges that they face a little bit later with some very concrete examples. But before I move forward and I say how we can solve this problem, I'd like to say a few words about neural ODEs and ODE approximations in general, because they are very much loved by us in the machine learning community. We should note that if it is for us to use methods such as this to learn through ODEs from data in the form of a function approximation, either using neural networks or Gaussian processes, then the discover functions are not closed form. So this type of algorithms do not solve the task we have in mind, because they do not provide us with a real equation. So they are not suitable also for chaotic system, where a small variation in the initial condition may lead to a big variation. And additionally, the optimization step may often require, in this case, also dealing with very complex problems. But again, the most important disadvantage of this is that we do not have a closed form expression. And hence, in terms of discovery and in terms of interpretation for scientists, this is not enough. However, let me just say that if you are using these methods for other purposes rather than discovery and interpretation, then another method that you may want to take a look is a method that we are going to present next week at ICML 2022 that significantly outperforms neural ODEs. We call this method neural Laplace, and we believe it's a powerful extension to neural ODE. Now, let me talk about how can we solve this problem. So we create Decode to address these challenges. And this work that we call Decode is built on the following side, on the fact that the variational formulation of ODEs is enabling us to establish a direct link between the trajectory of X and the ODE, while bypassing the unobservable time derivative. So this type of insight, it enables us to develop a novel objective function based on this insight, and we prove that this is a valid proxy for estimation error of the true but unknown ODE. So if you are interested, Decode is an iClear 2022 paper developed by Zhao Zhen, Christophe, and me. So how does this really work? Let me briefly remind you that in order to really employ and use this variational formulation of ODEs, we are introducing a special functional that is going to be taking this function f, the trajectory x, and the so-called testing function g. And to understand how and why Decode works, we need to familiarize ourselves a little bit better with this variational formulation. And this will enable us to characterize an ODE without the need to refer to the derivative like the existing methods do. The value of the functional is the sum of these two integrals. And it is important to note that this expression does not depend on the derivative of x. What it does involve is the derivative of g. And if we choose g in such a way that the derivative is easy to compute, so we select g, g is now something that we can design, and I'm going to talk about the design of g in a little bit, then if we can select g in a way in which the derivative is easy to compute, then calculating the entire functional is becoming easy. The variational formulation of the ODEs now state that the differential equations are able to hold if and only if the corresponding functionals are equal to 0 for all testing functions that are continuously differentiable and vanishing at endpoints. I'm not going to go into the details of this, but the reason I would like to highlight briefly this theorem of the paper is that this function is a core element of our objective. And we are going to show in a little bit that we expect that minimizing the value of this functional should correspond to finding better approximations of the true ODE. Let me show you first, though, how the Decode algorithm proceeds. It has two steps, a pre-processing step and an optimization step. In the pre-processing, we take the data set of the observed trajectories and we denoise them and we interpolate them to get estimated trajectories. Note that we can estimate these trajectories and not the derivatives. So our framework is agnostic to the exact kind of smoothing algorithm that you may want to use, and you can use that depending on domain knowledge or based on the application and the type of data you are dealing with. Then we aim to minimize this novel objective I introduced in the previous theorem, and this consists of the functional that I defined earlier. And we evaluated on all the estimated trajectories from the first step and all the pre-specified testing functions. And the actual optimization can be done by any algorithm that can be suitable for symbolic regression. As I mentioned earlier, we expect that minimizing the objective should correspond to finding better approximations of the ODE. And we make this formal in the paper. But what I'd like to highlight to you here is that in addition to providing this theoretical justification for the algorithm, the reason this theorem is powerful is because it guides us to select, how to select the choice of testing functions. And what we note on the basis of this theorem is that we should choose functions that form a Hilbert basis for the L2 space that are continuously differentiable and vanishing at endpoints. There are many functions we can use, but one particular natural choice is the Fourier sign basis. So we chose that in Decode. Now, we evaluated Decode and compare it against two-step symbolic regression and a variety of methods in symbolic regression, total variational regularized differentiation, spline smooth differentiation, Gaussian process smooth differentiation. And we looked first at the TOE example, an example where we have the knowledge, we have the dynamical system that is known, but we do like we don't know it, and instead we have the data associated with it. And we are trying to learn using Decode, but also the benchmark methods, what is the dynamical system. The reason we chose these particular examples is that they highlight different challenges that we need to solve in medicine. For instance, we use the Gompertz model and the generalized logistic model, because they are capturing asymmetric growth with saturation. And this is very often the case in medicine. We really often have asymmetric growth with saturation, for instance, when we have tumor growth or we need to model immune response. And what you can see in these results is that the decode achieves comparable performance in the low noise and small small step sizes, where the time derivative x can be accurately captured from the observed trajectories. But where we have a lot of gain with decode is under more challenging measurement settings, when we have increased noise, for instance, or increased step size, when we don't have a lot of observations. And in this case, the success probability of decode to learn the true equation is much higher. So again, this is not about prediction, it's about unraveling the equations that have generated this data, these different samples, and learning them from data. Also, we are able to show that decode is robust to measurement noise for both systems that I showed before, but also for chaotic and non-periodic systems. And that's really important because in medicine, we have many chaotic and non-periodic systems. And what you can see here is that while the benchmark performs relatively well when the measurement noise is low, decode is doing a lot better in settings where we have a little bit more noise or quite a lot of noise. And you can also see here that both symbolic regression, but also neural ODEs are failing to capture the behavior of the system. And again, another failure of neural ODE is the fact that we don't even have a real equation associated with it. Now, can we use this to do something really useful, something we don't know? Can we learn about something we are going to try to learn from data directly in medicine? And the example that we chose is coming from cancer, where we are trying to discover the temporal effects of chemotherapy on tumor volume. And what you see here is how the tumor volume looks like in the observations in the data sets, where it decreases initially in response to a particular type of treatment, such as chemotherapy, but then it grows again due to resistance to the drug. So we often have that tumors become drug resistant after some time. And while multiple models exist and have been published in numerous Nature papers for unintervened tumor growth, the cutting edge frontier in science is to really provide powerful and interpretable models that can capture the effect of drugs such as chemotherapy on the possibility of relapsing. So we have used, to be able to learn such information from data, a data set that was used in this paper of Gang et al., which represents 8 clinical trials on cancer patients taken in different types of environments, in different types of settings. And it represents the trajectories of tumor volumes measured over duration of a year of the patients that were enrolled in these clinical trials and were given chemotherapy. What we have done then is we have compared decode against a variety of models, but the interpretable, among the interpretable ones, the most powerful one was symbolic regression, or this two-step symbolic regression. And what you see here is that there are 2 big challenges associated with doing so, as opposed to decode. Unlike decode, symbolic regression learns a much more complex equation. So you see that decode learns something simpler and less complex. But more importantly, decode is able to predict the fact that we are actually going to have a relapse after chemotherapy, while symbolic regression is not capable to make this prediction that under no further interventions, the tumor volume would keep growing. So this is completely missed by this particular model. Now, I talked about decode, and again, I feel that this is an important milestone in this learning governing equations on the basis for data, but a lot more can and should be done in this agenda. Decode represents, in my opinion, just the very first step. There are many challenges to be overcome. One of them was to learn partial differential equations from data. And recently we have archived a paper that we call Decipher, again with Christophe and Zhaoji, where we are learning from data PDEs, which are even more complex than ODEs. Again, these are just beginning steps in this agenda, and I hope many of you who are now in the audience will join us and try to really develop powerful tools using machine learning to discover equations from data. Now, let me summarize what I've talked about today. So if it is to engage with users, what they would like in terms of explanations is, on one hand, they would like explanatory patient features, but they would like that not only for static predictions, they would like that also for time series predictions. And I introduced Dynamask as a first way to do that, but I think a lot more is needed. Unsupervised explain using feature importance, unsupervised models, as well as come up with example-based explanations. Then also another frontier is how can we really interpret and explain heterogeneous treatment effect models, so IT models. Can we really come up with interpretability methods for more complex problems such as that? And again, we recently put an archive together with Alicia, Jonathan, and Ioana, a paper that is starting, makes a first attempt to thoroughly look at the complexity of this problem. Then, as a second step, I talked about personalized explanations using a corpus of examples that's selected by a user, for instance, a clinician. And I introduced simplex as a way to provide such explainability. And finally, I would say at the very cutting edge of scientific discovery in medicine and beyond, we need to discover not only relationships and causal models that are qualitative, but also we need to have quantitative equations that are really unraveling complex physiological processes in medicine, but also in many other areas of science. And I would say there, a lot more needs to happen and a lot more needs to be done. And I just showed to you a first step, which is this decode framework, which is a powerful first step to start to think about these problems that goes beyond symbolic regression and yet is capable to discover such equations from data. Now, if you want to read more about what the clinicians want and the discussions we have with them, I've summarized that in a little blog post that captures the discussion, but maybe even better, you can look at the discussion I have had with the clinicians, either in Revolutionizing Healthcare or in my Turing talk. And of course, you can reach out and we can talk more. Or if you want to engage with my brilliant students, we have also an engagement session for academics and industry interested, especially in machine learning for healthcare. And in the month of April and May, we have had two very interesting sessions dedicated to causal deep learning, where we present some ideas and engage with industry on this agenda. And we invite you to join us in subsequent inspiration exchanges by subscribing to this engagement session and joining us and discussing not only with me, but also with my students. Thank you. I guess there may be some questions. Oh, thank you. I can hear that.
Any questions from the audience?
I'm sorry, I do not hear. A little better. Yes.
So I think some ways of comparing different interpretability methods on the same model for the same problem, and also maybe on.
I'm sorry, I still do not hear.
Better now?
I hope so, yes.
So the question is, are there ways of comparing different interpretability methods for the same model? And also, does it make sense to talk about it for different models and same problem?
Different interpretability. Would somebody maybe repeat the question closer to me?
Can you hear me now?
I hope so, yes. Seems better.
Different interpretability models.
About different interpretability models?
Compare different interpretability methods in the same model. How do you do that?
Oh yes, thank you so much. Yes, ideally, you would like to provide all these different facets of interpretability for a new model. So ideally, you would like to take a black box model and interpret it using feature importance. You can interpret it using example importance. You can choose a corpus of examples. And ideally, you can have real equations associated with the predictions. It's interesting to me that there is not one size fits all. If you look at the discussions with the clinicians, you'll see that different clinicians want very different things. Some of them want to know what they don't know. So, and they say so, these are the clinician scientists that would like that you tell them something new, that there is some type of discovery that's done on the basis of machine learning. Some other clinicians want real example-based explanations, but they would like that these explanations can be debugged by them on the basis of what they know. And also often they may be afraid that this model was trained in another population, potentially in another hospital or in another country, or maybe with some biases. And they want to interrogate the model on the basis of the current patient they have in front of them and related patients they think are relevant to the current patient. And be, let's say, be made feel comfortable about this. And then feature-based interpretability will still remain a workhorse of let's say, of interpretability for many. So I think it's really engaging with the user community, which in my case is the clinical community, especially clinicians, because they are the users of these models. But depending on who you are working with, different models may have different types of values. So for instance, if you are interested to collaborate with physicists, they may be much more technically and mathematically oriented, and for them, real equations may be the frontier, and they may want explanations that are really this closed form, compact equations that they want to unravel. So,
Hi, can you hear me?
yes.
I've got a bit of a tangent to go on. Given ethical considerations in clinical trials and GDPR and data protection laws, does that factor into the way you design models, because you've got to have the option of removing patient data as requested? So does that actually factor into how you design these models?
I do not hear you completely, but I heard partially, and there was a reference to GDPR and how they would like such models reported. I'd like to start by saying that this is why we developed the symbolic metamodels approach, because GDPR has their own standards, but it's even going beyond GDPR, that for many committees, for instance, this Joint Committee on Cancer in the United States is even stricter than GDPR in terms of what it requires from a model. And they really were mandating having not only a very clear analysis of the model failures, predictions, uncertainty estimates, but they also wanted true equations. They really wanted to see equations associated with this. So that's an example of a method that came out of a necessity. We initially had a method that was working very well, and the only thing that prevented, let's say, adoption was this type of symbolic metamodeling method being invented, if you like, to create these equations for the model. So I'd say, are we able to fulfill a lot of the GDPR constraints and requirements? The answer is, I think, yes, but there may still be some that are not addressed by interpretability methods, fairness methods, explainability methods. And it is exactly engagement with this type of forums that enables us to invent new things in machine learning. You know, it's necessity that's the mother of invention. So the reason, again, I'm very interested in medicine is not only the societal impact, that's definitely the main driver, but it's also the fact that it pushes my lab to come up with innovative ideas out of necessity of responding to challenges such as the one posed by GDPR. And I hope I inspire some of you in the audience to look at machine learning for healthcare, not as an applied field, but rather as an exciting field where a lot of problems are unaddressed and require your bright minds to engage with, to solve problems. Again, like dealing with GDPR regulation.
Sorry, can you hear me?
Yes.
Hi, I'm really inspired by the pipeline you're trying to build, where you have you try to basically learn which features is very important to use as an input into your symbolic models for the physical equations. But I have questions around how does your automatically ranking orders of the features take account of the dependency between features? Because sometimes you might have, for example, BMI is a function of diabetes, for example. How do you account that?
Yeah, so you are saying that I may have both categorical as well as continuous features. I thought you talked about BMI varying as a function of something like diabetes, which is more of or how one influences the other. Is that I'm not sure if it's a causal question you are asking or a way in which we can use these post hoc interpretability methods.
I think it's how does it capture the dependencies between the features when you're trying to find which one is important?
And I'm half hearing, half guessing, so I'm not sure I completely guess. But the way in which we are, for instance, in the symbolic meta models, we really learn these equations. But these equations, again, are at the lowest level, if you like, on the association causality ladder. So it's really a set of associative features that we are computing, and we are showing how they fit together to create maybe an explicit function that we can use for prediction and association rather than anything causal. The reason I bring the word causal there is the moment you are talking about BMI and diabetes, often people are maybe worried also about causal effects, and they can play a role. And this is part of very much of the machine learning agenda in healthcare. And again, that's the reason I pointed you out to these 2 engagement sessions we have had in May and April on causal deep learning. But with respect to the symbolic meta models, we are just using this purely as features, not as causality, or not as trying to really understand something causal there, but more just fitting these different functions, these different features and potentially perturbing features to see the effect on the prediction if we perturb these features. And if we have symbolic meta models, it's especially useful because we can show how even small perturbations may change the model's prediction. But again, if it didn't answer the real question, please drop me a line. Apologies, I don't know why I don't hear very well.
would be output of the explanation?
Was the word out of distribution mentioned there?
Unknown sample, if we, for example, have unknown sample, and then we feed it to the model, and we try to find, for example, the explanation. So what would be the mistakes? I mean, just like wondering what would be the output.
Apologize again. Could maybe somebody repeat briefly the question? Sorry for that.
So any questions? Can you hear me?
Yes.
The question was, how do these symbolic regression models or methods respond to out of distribution data?
Out of distribution data. So again, this is a good question. So often for so part of the reason we have presented these different views because these different methods provide you a way to debug the model, inclusively to debug the performance of the model and the adequacy of the model if you take it out of distribution data. For instance, if you do the simplex method that I described in the middle part of my talk, you can give examples that are out of distribution and see whether the explanations that are given make sense in the context of these out of distribution examples. And simplex allows you to do that with both features as well as examples. If it is about symbolic metamodels, you can look whether indeed the model extrapolates to these new areas, and you can see whether indeed these equations will extrapolate to these new areas. So this could be a way for you to really, let's say, debug the model. But what I think would be truly exciting and at the cutting edge, I would say, of what is being done today is not only to debug the model, but can you then improve the model? Could you then do something to improve this model? And that could be either by retraining the model, but that's maybe less exciting. Of course, you can retrain the model always. You can do something like lifelong learning, where you eventually could amend the model over time whenever needed. But maybe even more exciting would be, can you just add additional terms to the model to deal with this, this setting? Yeah. So if it is a question of just debugging, both simplex as well as symbolic metamodels are good ways to debug whether indeed the model will extrapolate well to this new setting. But if it doesn't, the question is, could you in an easy way now deal with this way and remain interpretable? How really to do that? I think that is something interesting there that's not yet completely understood and thought of.
All right, thank you very much. Yeah, thanks for the great answers and the great presentation.
Thank you.
I think this is the end of this presentation, so thank you very much.
Thank you very much. I apologize for not being in person. And if you have additional questions, please drop me an email and we can schedule a subsequent conversation where hopefully the audio will be much better.
Perfect, thank you.
Thank you. And I wish you a wonderful summer school. I hope you learn a lot and you enjoy being in Cambridge.